Welcome to Daily Papers, the podcast where we break down fascinating new research papers so you don't have to.
Today, we're talking about something that's on everyone's mind, large language models, or LLMs. These are the giant AI brains behind things like ChatGPT. They can write emails, generate code, create poetry, but they have a big problem.
And that problem is that they are, as you said, giant. Training one of these models from scratch costs millions of dollars and uses a staggering amount of energy. But even if you just want to teach a pre-trained model a new specific skill, it's a huge undertaking.
Exactly. Let's say you have a general-purpose AI, like a brilliant college graduate. Now you want to turn it into a specialist, say a lawyer, who knows your company's contracts inside and out. The traditional way to do this is called full fine-tuning.
That basically means you take the entire model with its hundreds of millions or even billions of parameters, and you retrain every single one of them on your new data. It's like sending that brilliant graduate to a full 4 years of law school. It works, but it's incredibly slow, expensive, and computationally intensive.
You'd need a supercomputer just to get started. So researchers came up with a clever workaround called LoRA, which stands for low-rank adaptation.
LoRA is a much more efficient approach. Instead of retraining the whole model, you freeze it. You don't touch any of the original parameters. Instead, you plug in a tiny separate adapter module. This little module has a much smaller number of new parameters that you train.
It's like instead of sending our graduate to law school, we just give them a small set of Cliff's Notes for the new job. You're not changing their core knowledge, you're just adding a small, specialized new skill. This is way better, reducing the number of parameters you need to train from hundreds of millions down to maybe tens of thousands.
But what if we could do even better? What if we could get that number down from tens of thousands to just a few hundred? That's the promise of a new paper from the University of Pennsylvania called QR-LoRA.
Right. The authors of QR-LoRA looked at LoRA and said, why are we adding new knowledge, even a small amount? The model is already huge and smart. What if the knowledge it needs is already in there somewhere and we just need to figure out how to access it?
It's a fundamental shift in thinking. Instead of adding a new set of Cliff's Notes, it's about finding the most relevant pages in the existing library of knowledge and just learning how to combine them in a new way.
So how do they do it? The name gives it away. QR-LoRA uses a mathematical technique called QR decomposition. Now don't worry, we won't get lost in the linear algebra here.
Please don't. The simplest way to think about it is this. QR decomposition can take a complex part of the model and break it down into its fundamental, most important building blocks or directions.
A good analogy is color. Imagine the model's knowledge is a very complex color, like a deep purple. QR decomposition is like a prism that can split that purple light into its pure primary components, a specific amount of red and a specific amount of blue. And crucially, it also tells you which components are most important for creating that color.
And these components it finds are what mathematicians call orthonormal. It just means they are independent and don't overlap. It finds the purest red and the purest blue, not a reddish purple and a bluish purple. It's very efficient.
So QR-LoRA applies this technique to the AI model. It analyzes the model's existing parameters and extracts the most important fundamental directions of its knowledge. And here's the brilliant part, it then freezes them. It doesn't change these directions at all.
So if you're not changing those, what are you training?
This is the coolest part. The only thing QR-LoRA trains are a handful of simple scalar coefficients. You can think of them as volume knobs. For each of those fundamental directions it found, the pure red, the pure blue, it just learns a single number, the setting for its volume knob.
So you're teaching the model a new task. You're not writing new notes of music. You're just telling it, turn up the brass section, turn down the strings a little. That's it?
That is it. You're just learning how much of each existing fundamental skill to use. And because you're only learning the setting for a few volume knobs, the number of trainable parameters plummets.
And the results they found are pretty mind-blowing. They tested this on a standard language model called Roberta Base, which has 125 million parameters.
Okay, so for context, full fine-tuning would mean updating all 125 million of those. The older efficient method LoRA would train about 92,000 parameters. Still a huge improvement.
But QR-LoRA, in one of their experiments, it achieved results that were just as good and in some cases even better than both those methods by training only 601 parameters.
Let that sink in. Not 125 million, not 92,000, just 601. That is over 1,000 times more efficient than full fine-tuning and about 150 times more efficient than standard LoRA.
It's tiny, but mighty. It gets the same or better performance with a ridiculously small number of trainable parts.
So what does this mean for the real world? Well, it makes customizing powerful AI models drastically cheaper, faster, and more accessible. You wouldn't need a giant server farm to do it.
Think about on-device personalization. You could have your smartphone's AI assistant adapt to your unique way of speaking or writing, right there on your phone without sending your data to the cloud and without draining your battery.
Or small businesses could afford to fine-tune a model to be an expert in their specific product catalog, creating a super intelligent customer service bot on a shoestring budget.
It really democratizes the ability to specialize these powerful tools, and it all comes from that clever insight. Don't add, reuse. Find the essential components that already exist and just learn how to mix them.
It's an incredibly elegant solution. Instead of building a new addition to the house, you just find the most important support beams and figure out exactly how much pressure to put on each one to get the job done. And it turns out that's all you need.
A great example of how sometimes the smartest solution isn't about adding more complexity, but about finding the simple, powerful patterns that are already there. That's all for this episode.
Thanks for tuning in to Daily Papers.